Hi friends, welcome to the channel Learning R is Fun. In our last video, we have seen probability distribution in general and the way in which R handles this probability distribution functions, cumulative distribution functions, etc. and how to make the density curves for a given data we have seen. In this video, specifically we will be addressing two distributions, normal distribution and Poisson distribution. Normal distribution is basically a bell-shaped curve, and under this bell-shaped curve the total probability is 1, that is any data lying between the third standard deviation from the mean. Then you will have 99.7% of the data lying in that. Between mu minus 2 sigma and mu plus sigma you will have 95.45%, and between mu plus sigma and mu minus sigma you will have 68.27% of the data. So basically the entire data lies between 3 sigma to 3 sigma distance, you can say. 99.73, you can assume it's almost 100%. So this is the 68, 95, 97, 99.7 rule, and we'll see some examples to understand this. And we'll move on. The Poisson distribution basically is a discrete probability distribution as compared to normal distribution, which is a continuous probability distribution. In this case, the probability density function is known as probability mass function, and here it's given as e power minus lambda into lambda to the power x divided by factorial x. Since there is a factorial x, you can understand x cannot be fractions, it should be integers. So that's why you are getting you can say a discrete probability distribution. And in the discrete probability distribution, sometimes the value what you get here out of this function can be more than 1. So basically what you are getting here, that's why you are seeing 1.6, 1.4, etc. So obviously this cannot be the probability, because probability cannot be beyond 1. So what is this then? It is a relative probability, as we have discussed earlier in the previous video. So probability density function or probability mass function may result in a value which is more than 1, but actual probability is the area under the curve, and that cannot exceed 1. In case of Poisson distribution, it is basically given number of events occurring in a fixed interval of time or space if these events occur with a known constant mean rate, that is your lambda, and independently of the time since the last event. So we'll see some examples so that the concept is clear. Now let's go to RStudio. For today's session, I have made two programs. One is normal distribution .r, other one is the Poisson distribution .r. We'll start with the normal distribution example, and here we have got a problem, that is the first year salaries of IIM graduates is normally distributed with the population mean mu, that is 2 lakhs, and the population standard deviation, that is rupees 50,000. Find the probability of a randomly selected IIM graduate earning less than 1,50,000 and more than 3,75,000 annually. This is the problem. We got mu, we got sigma, we got both the x values. We have to simply find the probabilities, that's all. So let us store these values. So we have stored mu, sigma, x1, x2. Now for the first case, less than 1,50,000, we apply a pnorm function. Pnorm function gives the probabilities. You have to give the quantile. In this case, quantile is the particular value, that is q1. You can say x1, 1,50,000, and then mu and sigma you are providing. So let's execute this. So we got a p-value of 15%. So 15.87% is the probability that somebody is getting less than 1,50,000 the first year. Okay. Now the same thing for 3,75,000. In this case, we have to do a little bit of work. That is, when you ask for pnorm x2 and you supply 3,75,000, then you get less than 3,75,000 in the normal curve, but you want more than. So what you have to do, you have to subtract from the total probability. That's all. You do that and you are getting a very less percentage. You can say 0.0002. That is, you can say 0.02 percentage. So that means there is almost none. Okay, we have got the quantiles, we got the probabilities. Suppose we are being asked, the probability is being given and we have to find out the values. That is the problem number 2. Find the range of annual salaries, the top 15% earners. Top 15% means we have to take the probability as 85% and then subtract. Okay, so we find out that is Q norm, and the top 15% means 85% of the people, the Q which is going to give you that value. So you are getting 251821, that is 2,51,821 is a minimum salary of the top 15%. For maximum, you have to give Q norm, and you need not give 1. If you give 1, you will get infinite. So you have to give something lesser than that. We will give 99.7%, that is 3 sigma distance. So here we are getting 33,73,889, that is 3,37,389. So we are getting a value between these two. These are the top earner salaries. We can just do a reverse calculation also. P norm, again instead of Q norm we will put P norm and find out what was the percentage. We will supply the same 251,821. We get a, this has not been executed. I have to keep the cursor here and execute. So we are getting 84%, 84.99, that is almost 85%. So we just verified the previous result, that's all. Now let us go and see the standard rule of percentages for first sigma, second sigma and third sigma. We'll create a random variable x and then we'll populate it with the random normal values 100,000. So 1 lakh values are there in x now. Large numeric is what you see in the environment. Now we'll create P norm of SDFX and P norm minus SDFX. Actually here we are finding the distance, we are finding the area between 0 plus SDFX, that is on the right hand side of the bell shaped curve, and P norm minus SDFX is 0 minus, because 0 is the mean here, because we have created the random normal values without mentioning standard deviation and mean. So basically this is 0 and 1, 0 for mean and standard deviation 1. X. So this is the first standard deviation distances and the area. We are getting 68%. Similarly for the second and third, we are getting 95, 97, 99.7. Basically it is 68, 95, 99 rule. So this is how we have got it. Now we can plot the density curve. When you are plotting the density curve, you are getting a normal curve. Now let us try to draw the ordinates, coordinates of x and y. We will separately write. When we are writing like this, what we are trying to do is, we are supplying the x coordinates of the line and y coordinates of the line. So we want to draw a line at the first standard deviation distance. That is one line here and then one line here. So here the coordinates are for x value, the first line, the coordinates x here is minus SDX, and for this line also, for this point also, the x coordinate is the same. That's why I have written minus SDX, minus SDX. So I got 2 quad x. Similarly, 2 quad y. Here I am getting for this point, the x value is already found out. Now we have to find out the y value for this point. For this point the y value is 0. For this point the y value is d norm of, d norm curve gives you that value. So d norm and SD of x. So the x value you have to supply to the d norm curve, then you get this. So you have done this x and y coordinates. Now let us make the lines. Lines basically you should not use line. Line is another function. So you have to use lines function. Give x coordinates and y coordinates, and then color can give red. So let us execute this line also. So we have got the line here. Similarly, I will draw the other line, the other side. So now this is the area which is encompassed between these two ordinates and the norm. This area is the area of the 68% we have talked about, the 68.34%. So now we will move on to the third problem. Here the children's IQ scores are given. Basically they are normally distributed with a mean of 100 and standard deviation of 15. The question is, what proportion of children are expected to have an IQ between 75 and 125? This is similar to what we did earlier. Only thing is I will do it little bit elaborately. Let's define these parameters, mean and standard deviation, and a lower bound and upper bound which is given in the problem, 75 and 125. Now we will create x and y values. X values I am going to create using sequence -4 to +4. Length is 100. That means I want a sequence of 100 numbers between -4 to +4, and that multiplied by the standard deviation plus mean. Here you can intuitively understand we are generally finding the area between 1 sigma distance from mean, that is SD plus mean, and minus SD plus mean. So that means on either side of mean we are getting this area. Now what we are doing here is, similarly we are trying to get various points, that is 100 points we are taking on left hand side and right hand side, 50 each, and then up to 4 standard deviations, and these are the x values. Corresponding y values you will get by denorm function. So hx is the height of the ordinate, that is nothing but the y point in the curve. So curve points can be obtained in the denorm function. So for each of the x we are finding hx also. So what is hx? We have seen that it is also 100 points. Now what we will do is, we will plot with the x's and y's which we have found out. And type I said no, that means I am not putting dash or dot or anything. So I will get only the template without any plot. Now I am going to draw the lines for all x coordinates and y coordinates. So I am getting the curve. I is defined now with all the points x greater than or equal to LB, that is above the lower bound, and x less than or equal to UB, that is the lower than upper bound. 75 and 125 upper bound and lower bound we have defined. In between these two, all the i's and all the points are stored in I. Here we have to note the i's are logical values, because we have asked the question x greater than lower bound and x less than upper bound. The x values we have defined earlier using sequence. Those points will be compared, and then those points which lie between LB and UB, that only will be stored in I, basically as logical values. Now once they are logical values, then you can use them in the index and get the actual point. This you have to understand. Now once I is stored, now we will create an axis. Axis 1 means bottom, and we are giving tick marks 42, 160 with 20 points each, that is a tick mark. Let us draw the polygon also. In the polygon we have to give x and y coordinates. The x coordinates I have given the lower bound, then all the x's, and then upper bound. Similarly for y coordinates I am giving 0, that is in the lower bound we are starting at 0 here, and then similarly y values keep increasing as per denorm, and which are available in the hx. So height of the ordinates which we already calculated, and those are nothing but the points on the curve. Again in the upper bound when we are reaching, we are taking x value as 0, y value is also 0, and color is red. So the polygon is drawn and we are able to see this is the area which is between 75 to 125. And now we have to find the probability for this. So probability for this can be found out P norm upper bound. So all this area right up to this point, and then again P norm of this lower bound, then you get this area. So this total area minus this area is going to be the area which you require. That is what is given here. So now area I am calculating, and now I am going to use a phrase, and then that I am going to put as the title. So paste, and I have included these things, and now M text is resultant 3. So I am getting the M text here. This is nothing but the title. So what I am saying is the probability I have calculated, that is nothing but the area, and that area I am including significant digits, 3 digits, so 3 digits. So 90.4% is the answer to this problem. That is, the question is, what proportion of children are expected to have an IQ between 75 to 125? The answer is 90.4%. Okay, now you have understood how a general problem of data which has got a normal distribution can be solved using simple OR commands. To visualize, we have utilized these statements. There is a test. Suppose you don't know the data is following a normal distribution or not, that test you can apply. The question mark Shapiro test. Test basically it is Shapiro-Wilk normality test, and performs a Shapiro-Wilk test of normality. Here you have to give numeric vector of data values, then it is going to find out. So now in our case we will give simple R-norm values 1000, 0, 1 data. Here the null hypothesis for this data is normally distributed. And once we create a data and then we will ask Shapiro-Wilk normality test to be performed, we are getting a p-value of 0.21. It is higher than 0.05. That means we have to accept the null hypothesis. Now we will create one more test for the faithful data set in which eruptions data is available. So we will ask. Here we are getting a value which is much less than 0.05. Therefore here we have to reject the null hypothesis. Now we will move on. We are going to Poisson distribution. In Poisson distribution, let us do a simple problem. In the World Cup, an average of 2.5 goals are scored each game. Modeling this situation with a Poisson distribution, what is the probability that k goals are scored in a game? Here lambda is 2.5. In a game, we get either 0 goals scored or 1 or 2 or like that. It can be up to 10 goals. We'll assume like that, and let us try to find out the probabilities. So first of all, we'll use a d Poisson. X lambda is mean goals, because this 2.5 we have stored as mean goals, and we'll arrive at d Poisson for this, all the 10 values or 11 values rather. Mean goals not found because it is not loaded. Now I will ask for d Poisson. I am getting 11 values. Then I am going to plot the d Poisson values with a line. So I got a Poisson line. Here we can also make a bar plot with the rainbow colors. So we are having for each situation what is the probability. The first is 0, therefore the probability for not scoring any goal is here, somewhere here, 8% you can say. Probability for scoring 3 goals, 0, 1, 2 goals is almost 26% or so. And then the probability tapers down. So basically this appears to be the maximum goals possible. So 2.5 goals is what is the mean, and we are getting a maximum in 2 goals as per the distribution. Now another problem. Here a statistician records the number of cars that approach an intersection. He finds that an average of 1.6 cars approach the intersection every minute. Assuming the number of cars that approach this intersection follows a Poisson distribution, what is the probability that 3 or more cars will approach the intersection? So in this case, P 2 or less we can find out by finding out 0, 1, 2 or 3 situations, and our mean is 1.6. So we get a probability for the 3 different situations, that is 0 car approaching, 1 car approaching, 2 car approaching, and we will sum this up. You can also see the environment. Here P2, we got 20% probability, 32% and 25.8. That means this means 3 probabilities are there for the cars, 0 car approaching, 1 car approaching, or second car approaching, 2 cars approaching. Now we have summed up this probability, and that probability will subtract from 1. So we are getting an answer of 21%. 21.66% is the possibility that 3 or more cars will approach. Because up to 2 cars, what is the probability we have found out, and we subtracted that from 1. So thus far we have seen certain practical examples using normal distribution and Poisson distribution. In statistical tests, we will be using t-test, f-test and the chi-square test, etc. That will be our next topic. Thanks for watching, and see you in the next video.